turbulence. And I have to say that here we are considering an Euler Lagrange approach for the simulation of fiber motion in the turbulence, and we still use or treat our fibers within the point particle limit. So I will explain how we did this in a moment. So I will fix just on, let's say, this work that we started 1.5 years ago in Udine, together with Diego Dotto, who is the PhD student who is performing the calculations. So that's the physical problem that we are interested in. So we are releasing a number of flexible fibers in a turbulent channel flow at, well, not very high Reynolds number. This is the shear Reynolds number based on the channel 8. And the reason for choosing this value was to compare with previous data sets that we had for spherical particles and rigid fibers, so to make comparisons. And we are interested in the effect of turbulence on the dispersion of these fibers, and in particular on macroscopic phenomena related to preferential concentration that inertial particles are known to undergo in such flow. So preferential concentration in the one normal direction and segregation in the DOR region. But of course, in this case, we are also interested in understanding the rotational and bending dynamics of the fibers. So to do so, we changed fiber inertia, which is quantified and parameterized by the Stokes number, and we changed the elongation of the fiber, which is represented here by the aspect ratio of the fiber themselves. In order to model the fibers within the point particle approach, we use a model that has been developed a few years ago, originally by Lindstrom and Uesaka, and then it has been used by other groups, which is the rod chain model. So our flexible fiber is nothing but a chain of rods which are connected with each other through some ball and socket joints. And here you can see just 3 segments composing the fiber. And for each of these segments, we solve for the following equation. So just first and second Euler's law. So this one is the force balance that is governing the motion, the translational motion of the fiber. So VR is the velocity of each segment composing the fiber. Now each segment composing the fiber is smaller than the Kolmogorov scale within the flow, so it can be treated as actually a point moving within the flow, but the full length of the fiber is longer than Kolmogorov. I would say several times longer than Kolmogorov. Now in this equation here, we are only considering the drag force acting on the fiber and the constraint forces between neighboring segments. Then this is the equation for the rotational motion, so we can get the angular velocity of each segment, which is subject to the hydrodynamic torques and of course to the additional torque due to the constraint force. And we have of course to allow relative rotation between neighboring segments within the fibers, but they cannot detach, they cannot translate from each other, so we are imposing a connectivity constraint on neighboring fiber elements. This is the orientation, the time evolution equation for the orientation of each segment within the fiber, and I'm showing this because that's the bottleneck in terms of time stepping that we have to use, and this is what makes the problem very stiff in that respect. And these are the values that, I don't know if you can see, that we consider for the Stokes number and the aspect ratio, which are always referred to the single element and or segment of the fiber. Now, just a couple of slides to show the expression for the drag force that we use. So if the particle, or actually the segment Reynolds number is equal to 0, we have an exact expression for the drag force, where this is the relative velocity between the fiber segment and the surrounding fluid. But in our simulations, we are basically always considering segments that have a finite value of the shear Reynolds number. So we are using this expression here, where CD is the drag coefficient, and there are some empirical correlations that you can use. So the details maybe should be discussed afterwards for sake of time. And for the hydrodynamic torque, we have 2 contributions. The first one comes from the fact that our fibers have relative spin with respect to the surrounding fluid. And so this gives one component for the torque. And the second component is given by the fact that the fibers and the elements actually are subject to the local rate of strain of the fluid. So these are just the expression that one can derive by integrating along the fiber length the force. Now, these are, again, just a summary of the simulation details. So in particular, we are considering 200,000 fibers, and here you have a close-up view of the fiber motion inside the flow. So here we are focusing in the nearward region, so you can have an idea of what our model provides in terms of dynamics of the fibers where they're close to the wall. And each fiber is composed of 7 segments or elements, and the statistics and the observables that I will describe are, let's say, converged with respect to this number of elements. So a larger number of elements would not change the statistics. And we have run simulations considering both one-way coupling and two-way coupling, because in principle the volume fraction and the mass fraction that we are considering on average would correspond to dilute suspensions of fibers, but because they have inertia, they tend to cluster somehow and segregate preferentially. So locally, this dilute flow condition may break, so we wanted to see what was the effect of including a force coupling between the fibers and the fluid. So just to show you right away what is the effect of this two-way coupling, not much, I would say, at least within the time window that we have analyzed. So these are just results referring to the fluid velocity statistics, so mean and RMS, within a time span, which is this one in time units, which is the one required for the flexible fibers to reach a steady state for concentration along the normal direction. And these are the details about the volume fraction and the mass fraction. Here we are considering the fibers with highest inertia, because these are the ones who are expected to give a stronger feedback to the fluid, and the results have been obtained considering not the standard particle in cell two-way coupling approach, but a sort of improvement of this, which was proposed recently by Gualtieri and co-workers in Rome, where you have some regularization of the drag force, which is feedbacking then on the fluid. So basically, in order to compute the feedback of the particles at time t, you must consider the drag force at some earlier time and allow the disturbance of the particle to diffuse in space over this viscous time epsilon r. So the details are given in the paper by Gualtieri et al., but again, these technical details and small details can be discussed later. But the main point is that you can see that there is no big difference between one-way, which are the lines, and two-way statistics, which are the symbols. And the same is true for the concentration. So this is the concentration for our reference set here. Again, no big difference. So you can still see some concentration close to the wall. I would say just outside the viscous sublayer here. And in fact, talking about concentration, this is one of the observables that we have been looking at. So we have seen already that there is the usual peak of concentration close to the wall due to turbophoresis. These particles are inertial, so they will undergo the same accumulation effects that small spherical particles or equivalent rigid particles would do. Here, I'm just showing an example of the concentration profile that we get. On the left-hand side, we fix the Stokes number and the elongation of the fiber, and we compare what our flexible fibers do in terms of preferential concentration with equivalent rigid fibers. So the rigid fibers have exactly the same physical and geometrical parameters of the flexible fibers, but they cannot bend. So that's the only difference, right? And as you can see, there is the main difference that we notice is that the flexible fibers, so the green curve here, can accumulate more easily very, very close to the wall. So we are here within 2 wall units from the wall. So it's it's a very thin region inside the viscous sublayer. And this is due to the fact that we think that this is due, well, we are still, let's say, investigating in detail this, but this is due to the interaction that these fibers have with the wall. So basically the flexible fibers can reach closer to the wall because they bend, and therefore they have a different type of interaction with the near wall structures, which are trapping actually the fibers at the wall. The rigid fibers cannot reach this very close, this very near wall region, and so they cannot be trapped as easily. That's to highlight the effect of fiber deformability, but of course on the background you still have inertia planes. So if you compare what different sets of flexible fibers do as you increase the inertia of each element, then you can see that the peak is shifting away from the wall. So the inertia of the fibers is high enough to push them a little bit away from the wall, and yeah, so the peak is also slightly decreasing. Once the fibers are in the near wall region, they are also undergoing segregation. And here in this animation, you can see actually the full domain, the full flow domain that we are considering. And what you see, these are actually the fibers that we are simulating. So that's the actual length. So they look like points, but they have some elongation. And the red and blue regions that you see here are the high and low speed streaks of the fluid. So you can see, as we have heard already today, that there seems to be an accumulation in the low speed streaks near the wall, and this is in fact what we get. So if you try to quantify this effect through some statistics, you can compute the PDF of the streamwise fluid velocity fluctuations seen by the fibers in the near wall region. Here I think we are considering only fibers within the viscous sublayer. And as I said, there is segregation in low speed streaks, but here what we are comparing is actually the relative tendency of segregation between flexible fibers and rigid fibers. On the left for fibers with lower inertia, on the right for fibers with higher inertia. And as you can see in both cases, the PDF of the flexible fibers, again in green, seems to be a little bit more positively skewed and shows higher probability of segregating in the negative semi-plane, so into the low speed streaks. So there is actually no qualitative effect of deformability on the behavior of the fiber near the wall, but only quantitative effects, as probably could be expected. Regarding the deformation of the fiber, so the bending of the full fiber, we have tried to quantify this considering the solid angle alpha, where here angle brackets indicate that's an average value of alpha that we are considering. So this alpha is measuring the relative orientation of two neighboring segments in composing a fiber. So if alpha is equal to 0, then the relative orientation is 0, so the elements are aligned. If it's 90 degrees, they are somehow bent, or yeah, the fiber is bent. Here I'm showing you 4 different lines. So these 2 lines refer to different aspect ratios fiber in the near wall region, so within a fluid slab of 30 wall units thickness. And here the PDF is relative to the same 2 aspect ratios, but only considering fibers that are in the center region of the flow. And as you can see, regardless of the length, so of the elongation of the fiber, we have a peak of the PDF near the wall at alpha equal to 0. Here the average was obtained over all elements of a single fiber and then over all fibers in the corresponding fluid slab. Whereas if you go in the bulk of the flow, there is a peak towards a finite value of alpha, which indicates stronger bending. Now here you can then correlate these 2 PDFs with the local mean shear, which is perceived by the fibers, which is actually kind of small for fibers in the bulk region and somehow higher for fibers in the near wall region. Now this is of course related to the effect of the surrounding fluid on each fiber element. So what I'm showing here is, let's say, are the constraint forces that are acting within each fiber. Okay, this is these two plots show these constraint forces as measured along the axis of each element for the fibers with smaller inertia in our flow and for the fibers with higher inertia in the flow. And as you can see, these constraint forces are higher for longer fibers. So it means that these fibers are more subject to tensile forces. And this is due to the fact that being longer, they experience different velocity gradients, which are, of course, induced in the deformation. And there is a clear peak, especially here, exactly in the region where we could observe a stronger bending, so near the wall. And if you measure the same constraint forces in the direction perpendicular to the axis, so these are the forces that would actually try to bend each element of the fiber, you see similar behavior, even though the values on the y-axis are a little smaller than before, meaning that our fiber are mostly subject to tensile forces rather than bending on each element. How much time do I have? Am I supposed to stop at?
No, I think you're good. You can speak for 7 more minutes.
7 more. Ah, okay. Yeah. So until right. Okay. So the solid angle was just one measure of the fiber flexibility. Then this is actually another one. So a way to measure how the fibers are bent by the fluid is to measure the end-to-end distance. So if the distance is equal to the fully stretched fiber length, then there is no deformation. If the fiber is bent, then this number or this quantity would be smaller. And here I'm showing you the mean value of this fiber end-to-end distance along the normal direction for 3 different sets of fibers. Okay, and I think here, yeah, we are considering also different elongations. So these are the longest fibers. So it's 11.75 wall units in length, which I think it's about maybe 7 times the Kolmogorov time scale, and this is 2 to 3 times the Kolmogorov time scales in terms of length. And as you can see, so that's the length when the fiber is fully stretched. This is the actual length that we consider. And as before, we see that if you look, for instance, at the higher inertia particles, near the wall, the fibers tend to be stretched because the end-to-end distance is closer to the fully stretched value, whereas in the center of the channel there is a decrease. And in fact, we see that away from the wall, this end-to-end distance reaches a sort of Oopla. Sorry, that woke you up for sure. I should have, yeah. I knew that I didn't have to go too close because, so I will stay here. Okay, so that was done on purpose, by the way. Okay, so at least I didn't fall. Okay, and yeah, what was I know I went back. Yes, yeah. So there is an asymptotic value in the central region of the channel where homogeneous more. I mean, the turbulence is closer to being homogeneous and isotropic. Now we also investigated the time behavior of the end-to-end distance, considering again different fluid slabs. So here you see again the fibers with different elongation. Here the green curve corresponds to long fibers in the bulk of the flow. Okay. Sorry, the green curve corresponds to long fibers in the near-wall region, whereas the black curve corresponds to the same fibers in the bulk of the flow. And here we have done the same distinction for shorter fibers. This is for low inertia fibers. So what you get is there is a decrease of the length. The fibers are initially seeded into the flow as fully stretched, and after some time there is a steady state value, which is reached also when we increase the inertia of the fibers. So that's what you get when you're considering the highest inertia. So the wall value of the end-to-end distance is always higher than the value of the bulk of the flow, confirming the fact that when inertia of the particle is increased, the wall and the mean shear that is acting on the fiber is acting to stretch them. There is a steady state that is reached, so we see no oscillation in the fiber end-to-end distance, which seems to indicate that there is no actually characteristic time scale of turbulence which is determining the behavior that we observe. This is somehow different from what it was observed in a recent work by Luca and Marco Rosti, where they considered a flexible fiber, which was actually much longer than the ones we are considering here, in a homogeneous isotropic turbulent flow. And they could observe some sort of oscillation that we do not see, so maybe this deserves further investigation. Okay, so these are the conclusions, and I would like to focus more on what needs to be done, so what we would like to do. First of all, we would like to explore further the force coupling effects by running longer simulations that we were able to do for the time being. Because the fibers are anisotropic in shape, so they are elongated, we would like also to include a full mechanical coupling. For the time being, we only coupled the two phases through force, but of course it would be interesting to see what happens when also torque coupling is considered. And in this framework, it would be also useful and interesting to account for bendy stiffness. So the fibers will be somehow stiff with respect to bending due to the underlying effect of the fluid. And so I think this would give a more realistic framework for our simulations. And of course, if we wanted to include or go to much denser suspensions, then we could account for fiber-fiber collisions. In the model that we have considered so far, the fibers don't see each other, but even the neighboring elements don't see each other. So they could, in principle, let's say, rotate and cross each other. In our simulation, that doesn't happen, but our model is not taking this into account. So that's, plan for the next couple of years, maybe in the next conference, there will be something more to say about this. So that's it. Thank you very much. And if you have any questions, I'll try to answer at my best. Thank you very much.
Thank you so much for being on